we're dealing with periodic classification, well, my advice to all the students who are actually preparing for their exams is, for each and every lesson in chemistry, if you wanted to have a quick revision, right, you need to have a one-page single document. One-page single document which involves all the important points, whether it is theoretical or even if you can have some numericals also as models. The best thing what you're supposed to do is, for people who wanted to write the immediate exams which are on your head, my advice to them is each lesson, whether it's in physics or chemistry, you need to have a single page document, and the document must be having all the important formulae, all important points, as well as, for forming a base, you must be having the worked out examples that are given in the prescribed textbook, that is your NCERT textbook or any other textbook which you are actually about to write your exam, right? That will be the best thing for a quicker revision. Well, if you wanted to know the intense depth details of the concept, then I think sit, relax and listen to me carefully. And we are dealing with what? Periodic classification. And I wanted to remind you, I love to remind you rather, that every time when I speak of periodic classification, I would like to remind you to induce a degree of seriousness that I'm not giving you 100 elements and then I ask you to place them in an order. You're not placing them in an order in your groups, vertical lines and horizontal lines, and these are periods and groups. Absolutely not. That's absolutely not a good thinking to have. As I told you, you have infinite number of periods in a periodic table, mind you that. Well, I came to the conclusion that you have infinite number of periods because each period is said to be a shell proposed by Bohr, which is designated by the principal quantum number, which is designated by Bohr. Once you have infinite number of shells, you're supposed to have infinite number of periods because each period is a shell, right? And also you understand that we are not just throwing it out as you like, some there, some here and all. Remember, there are schemes, there are principles, there are rules that are driving the periodic table as a torchlight, you must understand, right? Two things important. Number one, first of all, the periodic table is incomplete. When the periodic table is incomplete for you, then I think it throws out an open research area for you. Go venture out, take out some, you yourself can actually discover an element and you come back to me. I have a place in the periodic table, you must understand, right? So that element which is not found out, its properties are known to us in advance, right? Because when the position is fixed, there is something which is common in that particular position which is there in the periodic table because it is driven by some principles, rules, and they behave as a torchlight. So two things are important. I love to remind each and every student that it's not as simple and as trivial as you think that, you have rows and groups and columns and that's how they are placed it for a decorum. No, absolutely not. It stimulates research, you must understand. The periodic classification basically stimulates research rather. And the second one, what I wanted to say is there are some schemes, rules and principles which drive what periodic table, right? And in that process, I was also telling you that, all the mode of activity of all these elements. Now, when I say mode of activity of all these elements, I'm referring to their physical and chemical properties of all the elements that are present in the periodic table. And let me tell you that all these are functions of atomic size. So the most significant thing in determining the mode of activities are the properties of these elements are absolutely nothing but what? Your atomic size. And that's where we started our periodic properties. And remember the periodic property, recollect, the periodic property is nothing but a property which repeats itself at what? Regular intervals. That's called a periodic property. And in which the most significant one is atomic radii, which we were discussing. And you remember, I think these are the periodic properties which we were discussing about, atomic radii, and we proposed operational definitions, that's covalent radii, metallic radii, and you have other van der Waals radius, and we proposed an operational definitions because we had issues with what? Atomic radii, because it seemed to be absolutely idealistic. The second one which we were discussing is electropositivity. Anyone should follow this sequence. Rather, you first define what is a periodic property. Then you frame a function. You frame a function in the sense it depends on what, right? And then when depends on what, then I think you need to go to the trend in the periodic table. That means whether it increases or decreases in a period or increases or decreases in a group, that you need to tell. So the first thing is first you define it. Second thing is you frame a function. That means it depends on what. Then go for the trend. That is how it varies in the periodic table, that is in the periods and the groups. And then fourth one is most important, which is linked to the exam. That's nothing but the applications of electropositivity. So basically we are discussing periodic properties, atomic radii. We have any issues with that. And we have gone in for several alternate operational definitions, because if you stick to this idealistic definition, we are not in a position to measure that. So alternately, operationally, I was proposing it to you 4 alternate definitions. It's covalent radii. And then van der Waals radius, you have metallic radius and ionic radius, right? And then we have electropositivity. Now, electropositivity is a periodic property which is exclusively mentioned in case of what? Metals, right? We don't do that in case of what? Non-metals, because electropositivity is simply a tendency to vomit electrons, and tendency doesn't have any units, right? And that discussions I have made. And then I was even discussing electronegativity. Well, electronegativity I was discussing, and in electronegativity, this is a term which is basically used for what? Basically used for non-metals, because this is also a tendency to attract an electron pair. So remember that in a bond, the tendency to attract an electron pair towards itself is also a tendency, so it doesn't have any units. But I think we have assigned numbers to each and every element in the periodic table such that you just mentioned that number. I think we can have the idea of the magnitude of the attraction or the tendency to attract electron pair. These things I have done it, and I request you to make a simplest of the document of each and everything which is given to you, right? And then the fourth one which I was discussing is electron affinity. Right, now what is electron affinity? If someone is asking you what is electron affinity, and mind you that electron affinity is nothing but love. It's love for electrons, right? So what we will follow the sequence. First, what we will do, we'll define, right? What is this? How do we deal with what? Periodic properties. This is how we deal. Now what you do is first of all define. When you define, then frame a function. Frame a function. Now don't get confused with this. When I say by frame a function, then means that on what factors does it depend? That what factors does it depend? That's framing a function, right? And then you have the third one, that is the trend in the periodic table. The trends in the periodic table, that is in a period and in a group, how does it vary? And then going in for the applications. Right? This is what is the sequence which you are following for all this. First define, then frame a function, then trends in the periodic table and applications. Now it's time for defining electron affinity. Before I actually go in for that, mind you that electron affinity is also a word which is used for what? Non-metals and not for metals. It is ridiculous on your part to say, right, the electron affinity of a sodium, electron affinity of what? Cesium, rather than you speak in electropositive terms, not in terms of what? Electronegativity, sorry, electron affinity, you must understand. So it's time for defining. So I draw the attention of everyone and I define what is electron affinity for you, right? What is electron affinity? This is the definition. We are following the sequence. What is electron affinity? Is basically energy released. It's basically energy released. It's not absorbed. It's never absorbed. It's never absorbed. It's energy released. So electron affinity is basically an exothermic reaction. Exothermic reaction, you must understand. It's exclusively exothermic rather. Right? So energy released when an electron is added to an atom, right, or to an element. You must understand this. Right, energy released when an electron is added to an atom or to an element, you can say that way. Right, if this is the case, then energy released when an electron is added to an atom, then I frame a sequence for you. Right, I frame a sequence for you. Remember that it implies that if the added electron, right, watch carefully here. I'm defining what is electron affinity. Electron affinity is a energy released. It's an exothermic reaction. It's exclusively exothermic. You must understand, if you have the affinity, you're always what? Exothermic. right, when an electron is added to an atom or an element, right? If that is the case, if the added electron is held tightly by the nucleus, right? So if the added electron is held tightly by the nucleus, then more energy released. That means that it is more affinity, you must understand. It's more affinity. So remember, I'm trying to frame a function. This is defined. I defined what is electron affinity. Now I'm trying to investigate on what factors does it depend. And in the process, if you actually see, if you add an electron, if it is held very tightly by the nucleus, if you add it, it's an electron which you're adding, it's a negatively charged. When you add it, someone is catching. The only thing which catches the electron is, of course, what nucleus, which is positively charged, right? So if the added electron is basically held very tightly by the nucleus, then more energy is released. And remember, it will be held tightly. It will be held tightly only when the size is less. You must understand, when the size is less. So if the size is less, I think when the added electron is held very tightly by the nucleus, because when the atomic size is smaller, I think you are the nuclear force of attraction would be greater, and the moment you add it, I think you are actually catching it. If that is the case, then again we are boiling down to the same thing. That's nothing but electron affinity is basically again a function of size. It's again a function of size. Remember, we were discussing n number of periodic properties, and everything is becoming a function of what? Size. You must understand. It's a function of size. The size. So that's why I say if you have 100 and 120 odd elements in the periodic table with different properties, what is the fundamental thing which is varying in all these 120? Then I would like to say simply size. You look into this, even electron affinity, right? Electronegativity, electron affinity, electropositivity are all functions of what? Size. It's basically the size matters. When it's bigger, you have a different mode of activity. If you're smaller, you have a different mode of activity for that particular what? Element. Now, if you look into this, the energy released when an electron is added to an atom, right, that is electron affinity. It's an exothermic reaction. And what I'm telling is, if the added electron is held very tightly by the nucleus, then more energy is released. More energy is released in the sense you have greater affinity for what? Electron. When you add electron is held very tightly, it indicates love. And very tightly, it indicates more love, more affinity. And more love, more affinity, more energy is released. It's a common sense, right? So then I continue telling you that it will be held tightly only when the size is smaller. When the size is smaller, the nuclear force of attraction would be higher. So when you add it, I catch really tightly, and then more love, more affinity, more energy is released. That's nothing but what? Electron affinity. So finally, it's basically electron affinity is a function of size. And if you wanted to have a perfect relation for this, I think electron affinity is inversely related to size. You must understand. It's basically inversely related to size. So ultimately, again, we are coming back to the size, which is extremely important. So if I can put it in a sequence for you, let me put it in a sequence for you, then we'll go for its applications. Now remember, what is electron affinity? Watch carefully here. What is electron affinity again? So basically, electron affinity, I draw the attention please. Electron affinity is a function of size. And in fact, electron affinity is inversely related to size. So it's basically smaller the size of an atom, right? The nuclear force of attraction would be higher. So the moment you add the electron, it's held really tightly by the nucleus, indicating natural love for the electron. Natural love for the electron, greater love, more affinity, more energy released. So the magnitude of the energy released depends upon the more tightly the nucleus is holding the electron which you are adding. And that will be seen only in the case of what? Smaller size. And common sense is, I think in the periodic table, when you move from left to right and go to the extreme right top, that's where you have smaller sizes, because left to right the size decreases. left to right, the size decreases. So you can actually go and check for smaller size atoms to the extreme right, and I'm referring to halogens which are placed to the extreme right. You might ask me, why not, why not the noble gases? You can say noble gases, but noble gases have no affinity for electrons, at least under normal conditions, you must understand. So we have a separate chemistry for noble gases, but I think when you're going to the extreme right, you're almost going to the 17th group, you must understand. Right? If that is the case, if this is the case, then I think you can say in periods, the size decreases, then electron affinity increases. Electron affinity increases because the size is decreasing from left to right, so the electron affinity will increase. Similarly, in groups, I think the size will increase, so the electron affinity decreases, you must understand, because both are inversely related, right? That is the trend. Now, these are the simplest of the things which you were told in your classes. There is nothing new in this. But people who are listening for the first time, let me tell you that all periodic tables, we will be actually concluding it as a function of what? Size. And remember, the size is the case which will determine the mode of activity or the properties of a particular what? Element. You must understand this. If this is the case, then it's again inversely proportional to size. These are the trends. Now let's go in for an application and check out how this will vary. Let's take up an application, right? Watch carefully. These are the questions which are asked in exam. The very first question which people ask me, the very first question what people ask me is, if electron affinity is a function of size, well, I draw the attention of everyone. When I draw the attention of everyone, this is a question, there is a discrepancy. Rather, I would like to call this case to be a discrepancy. What I will do is, I will rather write this to be a discrepancy. A discrepancy in the trend. A discrepancy in the trend. Discrepancy in the trend. Say all discrepancies are, the questions that are important. All important questions are those which deviate from the normal trends. That's why they are important. So when I say discrepancy in the trend, this discrepancy is an important question in exam. If this is the case, what is the discrepancy? Well, it was said that electron affinity is a function of size. In fact, people told me that electron affinity is inversely related to size. This is what is the truth. If this is the case, then the size of fluorine is actually what? Is actually lesser than size of chlorine in the 7th group. Size of fluorine is basically smaller compared to what? Chlorine, and it's very obvious for you. You know very well, because chlorine is placed below the fluorine in the periodic table in the 17th group, right? So naturally from top to bottom size increases, and chlorine is a bigger atom compared to what? Fluorine. So the size of fluorine is less than size of chlorine. Then if that is the case, then if you put this trend here, then electron affinity of fluorine must be greater than the electron affinity of chlorine. Naturally, it is you have framed the equation, right? Now, if size of fluorine is less than size of chlorine, then electron affinity of fluorine must be greater than what? The electron affinity of chlorine. This is the expected trend. This is the expected trend, right? But the real trend is, the electron affinity of fluorine is basically smaller than what? Electron affinity of chlorine. You must understand, this is the correct trend. This is the correct trend, and this is discrepancy. That is the discrepancy. You must understand. Well, we are confused here, because when we look into such discrepancies, we think that what we are telling is might be what? Wrong. No, absolutely not. Discrepancy is one-off case here and there, and there is a reasoning for that. Well, I put it in a proper fashion. Observe carefully. Now, you said that electron affinity is a function of size. right? And electron affinity is inversely related to size, right? If it is inversely related to size, this must be the case. This is the size. I think everyone will agree with me. But electron affinity of fluorine must be greater than what? Electron affinity of chlorine, because it's inverse relation. So that is the expected trend. But the actual trend, if you actually see, the electron affinity of fluorine is lesser than what? Electron affinity of chlorine. And people must be asking questions, and you must be reasoning with me. Before you reason, I just put it, write the question for you. In fact, I would like to extrapolate and write it here. Right, watch carefully. In fact, the highest electron affinity, highest electron affinity is for chlorine and not what? Fluorine. Highest electron affinity in the entire chemistry, in chemistry, in fact, the highest electron affinity in chemistry is for what? Chlorine and not for fluorine, even though fluorine is smaller in size. We wanted to know that. Why? See, first, I wanted to tell you that, both are great lovers for electrons, both fluorine and chlorine. They love like hell, right? But the love of fluorine towards electron is slightly, don't overthink that, fluorine is hating electrons and chlorine is loving the best or something like that. No, absolutely not. There might be a discrepancy. But understand that fluorine is a non-metal, chlorine is also a non-metal, right? Both love electrons like hell. They love like hell. They love the electrons like hell. But the problem is, the love for electrons for fluorine is slightly. It is slightly. Don't overthink. Don't discount the love of fluorine. In fact, let me tell you that love for fluorine is almost equal to the love for chlorine. You must understand that. But the value slightly falls below chlorine. Very slightly. Well, I'm trying to induce this into you, because what happens is when I write such sweeping statements, people go, have a prejudice towards fluorine that it's not loving electrons. No, absolutely not. Both are great lovers. Fluorine and chlorine, both are great lovers. And let me tell you, the electron affinity values are just a few units here and there for what? Fluorine and chlorine. You must understand, great lovers. But the electron affinity fluorine value is falling below chlorine, and we have to reason for that, but don't have any prejudices that it's a bad lover for what? Electrons. No, both are equally good lovers, right? Let's reason for that. Before I reason, people who have just, wanted to know more clearly, for them, I'm telling you, electron affinity must be a function of size. There is absolutely no second thought on that, right? Electron affinity is inversely related to size. Yeah, of course, yes, it should be inversely related to size. But what happens, one discrepancy will be there. One discrepancy, I call to be a discrepancy, because it's deviating from the normal trend. It's one discrepancy, not everywhere, right? Only one discrepancy which we would like to mention. This is what is the case. The size of fluorine is lesser than size of chlorine, because chlorine is below what? Fluorine in the group of the 17th, right? And this is the case, then electron affinity of fluorine must be greater than electron affinity of chlorine, because both are inversely related. That is the expected trend. But there is a discrepancy. I call this to be a discrepancy. And actually what happens, the electron affinity value of fluorine slightly falls below what? Chlorine, and we wanted to reason for that, right? In fact, I would like to write this, in fact, for you. In fact, let me tell you that the electron affinity of fluorine slightly, and I would like to underline this. For you. It's slightly, very slightly. Don't have any judgmental things about fluorine that it's a bad lover or something like that. No, absolutely not. Slightly falls below chlorine, and we wanted to reason that. right? This discrepancy has been asked in the exam n number of times, and you must be also knowing it, right? And why not? Let's see and give the reasoning for that, right? The only, if you wanted to use common sense, the electron affinity value of fluorine is slightly falling below chlorine. It indicates that the love for electrons for chlorine atoms seem to be much higher compared to what? Compared to fluorine. That is the only reason, obvious reason. That is the only reason. What else might be the reason? If you're not loving grade, I think your value will fall down, right? There is something happening in the case of what? Fluorine, where he couldn't love the same magnitude as the chlorine is loving electrons. So what is it? Let us check it out here. And I draw the attention of everyone. Watch carefully here. Watch carefully here. Watch carefully here, please. Watch carefully here. I am discussing a discrepancy. I am discussing a discrepancy. Now, what is a discrepancy which we are discussing is electron affinity of fluorine falls below chlorine. And can you tell me why? Can you tell me why, in spite of having smaller size? In spite of having smaller size for fluorine, still the electron affinity value falls below what? Chlorine. And we wanted to reason for that. Well, we would like to reason for that. Why not? Common sense is suggesting that, I think the love has slightly decreased in the case of fluorine. That is the only reason. Well, the general reason must be that. What else will be the case? If 2 or 3 points lesser than chlorine, why it has dropped? Because the love towards the electron for fluorine has dropped, obviously. But why it has dropped, we would like to give the explanation. Watch carefully here. Now, what I'm telling basically is, if you see fluorine plus electron, it's a great love, it's a great affinity. It's a great affinity. Don't doubt fluorine. Don't doubt it, because this has the smallest size. That has the smallest size. And when you have the smallest size, when you add an electron, it will catch like hell. It will catch. It has a great love. Here I write, great affinity, great love. And what happens is, it forms F minus, no doubt about it. It forms F minus. When you add an electron, it forms a negative charge, and then the energy is released. Let this be even. That's the electron affinity of fluorine. That is the electron affinity of fluorine, and it is exothermic, of course. And it is exothermic. But take the case of chlorine here. If you put electron, it also has great love. That's nothing but a great affinity. And it also forms C minus, and this is E2. And this is also exothermic, right? But what I'm telling is E2 seem to be slightly greater than E1. I don't say E2 is greater than E1. No, absolutely not. I'm not shouting this way. Just greater than what? E1, right? And why such a thing? Why such a thing? Here is an explanation given to you. You can see both are great lovers. In fact, rather, this is a bigger size. You must understand, compared to what? Fluorine. Right? The E2 is greater than E1. And in fact, chlorine is, in fact, having the highest value of electron affinity in the entire periodic table. You must understand that, right? If that is the case, why such a thing should happen? Let us take the case. Let us analyze this. And the reason is this. Look into the reason. Look into the reason. Now, fluorine is one of the smallest atoms. You must understand, it is one of the smallest atoms. Yes, it is the smallest, because left to right, the size decreases. And the smallest elements are found in the periodic table to the extreme right top. To the extreme right top. And to the extreme right top is, of course, what? Fluorine. So fluorine is the smallest atom, right? It is the smallest atom. Now, it is too small, in fact. It is, in fact, why I call this to be too small. Then, if I write its electronic configuration, F is 9, then it is 1s2, 2s2, and this is 2p5. Come on. That's the 9 configuration, 1s to 2s to 2p5. Right? 1s to 2s to 2p5. And if you like to write chlorine, which is 17, then it's slightly bigger. It's 1s to 2s to 2p6, 3s to 3p5. Wow. This is slightly bigger. And this is small. This is small. Well, I think you will agree with me. You will agree with me if I say this, that if the fluorine atom is smaller, right, then even the outermost shell 2p will be smaller. 2p subshell also will be smaller. See, if you are a short person, I think your legs will be short, or the other things also will be short. The other organs must be short. You cannot have a this much bigger heart for a this much per small baby. No. So, if a fluorine is small, even the 2p subshell is also smaller. So if I say chlorine is big, then the 3p subshell is bigger. It's bigger. Let's take the case of fluorine. Well, I would like to say, since fluorine atom is too small, fluorine atom is what? Atom as a whole is too small because it's placed to the extreme right top. Right? Fluorine is too small. It's placed to the extreme right top. Then even the 2p subshell, the 2p subshell, when fluorine atom itself as a whole is small, then even the 2p subshell is small. The 2p subshell is also small. On the top, comma, right, on the top, the 2p is accommodating 5 electrons already. It is 5 electrons already. You can see here the 5 electrons. And this is small. 2p is smaller. The fluorine atom itself is small. So the 2p subshell is small. The 2p subshell is small. And on the top, it's accommodating 5 electrons. If this is the case, if this 2p is smaller, already 5, and if you try to add one more electron, when you try to add one more electron, these electrons already present and the extra electron, they slightly repel. They slightly repel. Already we don't have space. Already the 5 electrons we don't have space. You coming again. Don't come. They're not stopping it. But what happens due to lack of space, they're almost like, some sort of repulsion. Some sort of what? Repulsion has been generated in 2p. So what happens, there is a critical point which everyone must understand. Fluorine will accept the electron, that's for sure. It will for sure. F minus is very much available. In chemistry, fluoride ion is very much available. That means it has the love for electron. But what happens, that love, which is supposed to be the highest in the periodic table, slightly diminishes for the simple reason, right? Slightly diminishes for the simple reason. Fluorine is the smallest atom. Then the 2p subshell is also small. And on the top you have 5 electrons. You are supposed to push the 6th one into it. So the already present electron generates some sort of what? Repulsions. You come down, but such ferociously they are not doing it. Right? They are not telling, come. It's like, you're actually telling, okay, we also have no spaces, but still, that is the body language which is being used. You must understand. Then what happens, the ferocity of the love which we expected from the smallest atom slightly decreases, and thereby you can actually see slightly ripple. Then what happens is the electron affinity value actually what? False. Actually false. So how do you explain this? How do you explain this entire phenomena when is asked? Because sometimes theoretical questions are being asked. Which of the following is true? Which of the following is true? It might be the question. So how do you answer this? Right. Well, I would like to make a statement for this. Well, I would like to rewrite this for you. Why then? I think let me rewrite this reasoning for you such that you remember well. You remember well. Well, this is what is the reasoning why electron affinity of fluorine lesser than chlorine. The reasoning, if you see the reason, fluorine being the smallest atom, comma, the 2p subshell is also small, accommodating already 5 electrons. Already what? Accommodating 5 electrons in a small space. Then the addition of extra electron generates slight, I would like to underline the slight. Don't have a judgmental feeling that fluorine is a bad lover. No. It's not a bad lover. It's a great lover. It is actually it slightly generates slight repulsions. Then the 2p, which already has 5 electrons, and if you try to add the 6th electron, right, this and this are basically, these are generating what? Repulsions. Thus, electron affinity of fluorine falls below chlorine. You must understand. On the other hand, if you wanted to speak in terms of what chlorine, then you can simply say the chlorine is bigger and the 3p subshell is greater than what? 2p subshell. You can actually see, I can write it like this. The 3p subshell of chlorine is greater than the 2p subshell of fluorine. The 3p subshell of chlorine is greater than what? 2p subshell of what? Fluorine. Thus, you can say electron affinity of chlorine is greater than what? Electron affinity of what? Fluorine. You must understand that the other way, the other version, you can actually write it like this. You must understand this. So understand the question. This is a discrepancy. Now, you know, when we measure, we go to the lab, and you know, when we listen to the theory, our professor is actually telling us that fluorine is the smallest atom, and the electron affinity of fluorine must be the highest in the periodic table. With that mindset, when you actually go to the lab and actually try to find out the electron affinity of fluorine, it is few points lesser than chlorine. It's few points lesser than chlorine. Very few points. And we need to give an explanation. Come back again to the room and ask ourselves why there is a drop in few points of what? Electron affinity. Then I think the reason must be, I think the 2p subshell is too small to accommodate the 6th electron. Thereby, there is no great force of invitation. There is absolutely no great force for invitation. They are just inviting like this. You come down. They are not saying don't come. If it's don't come, then no love. No electron affinity. It's just simply saying we don't have space. Anyway, you have come down. Please come down. That's not the case with fluorine. Yes, it's inviting it. Yeah, please come down. Right? So it's also not shouting. But I think a few points have come down for the, in case of what? Fluorine. You must understand that is one way of answering. But otherwise, if you wanted to answer technically, you must understand the 3p subshell of chlorine is greater than the 2p subshell of fluorine. That's why the electron affinity of chlorine is greater than what? Fluorine. In fact, I would like to write, in fact, chlorine has highest value of electron affinity than what? Than anyone electron affinity in the periodic table. In fact, the chlorine has the highest value of what electron affinity in the periodic table. You must understand that. Now what we will do after, the great explanation given to you, electron affinity, I hope you followed. And then what we'll try to do is link this electron affinity to your exam. To your exam. That is nothing but what? Applications of electron affinity. Applications of electron affinity. This might be the case. Right. In this, what we will do is remember and recollect that electron affinity, basically electron affinity is told for nonmetals. It is basically told for what? Nonmetals. So the electron affinity is the language which people use it for what? Nonmetals. You must understand this, right? If nonmetals is the case, then remember, right? Nonmetals, well, I am quoting some synonymous statements. Synonymous statements. I am giving some synonymous statements to you. Watch carefully. Nonmetals have affinity for electrons. Well, if this is the case, when you love an electron, you pull the electron from your neighbor. Remember, this statement needs to be understood properly. When you love electrons, you try to pull the electron from your neighbor. So your neighbor is losing the electron. So it's getting oxidized. And you are reducing yourself. You must understand this. When you love electrons, you try to pull electrons from your neighbor. So neighbor is actually losing what? Electrons. When you lose electrons, you get oxidized. That's how oxidation is defined. Loss of electrons is what? Oxidation. And when you gain electrons out of your love, you're reduced. So simply speaking, I just put it like this. Let us actually go in for oxidizing power. Oxidizing power. You must understand. Oxidizing power. Now what is oxidizing power? If you love electrons from your neighboring atom, then the atom gets what? Oxidized, you get reduced, and you have the great oxidizing power. Well, I would like to say oxidizing power, I think you will also agree with me. That oxidizing power must be a function of electron affinity. It must be a function of electron affinity. Oxidizing power must be a function of what? Electron affinity, you must understand. Right? In fact, the more the love for electrons, more should be the oxidizing power. So the oxidizing power must be directly proportional to electron affinity. You must understand. Greater the electron affinity for the electron, more should be the oxidizing power, because the more you love the electron, I think more you are pulling the electron from your neighbor, and your neighbor is getting oxidized and you are oxidizing it, hence you are called an oxidizing agent. So the oxidizing power, basically the oxidizing power would be more if the electron affinity is more. If this is the case, then I'm actually telling you that oxidizing power is a function of what? Electron affinity. In fact, the direct relation is existing between what? The oxidizing power and electron affinity. You must understand this. Now, if this is the case, then obviously the electron affinity of chlorine is the highest in the periodic table, and at least for if I compare chlorine with what? Fluorine, I think the electron affinity of chlorine must be greater than what? Electron affinity of fluorine. At least that is what we were discussing from the last 15 minutes. Right? Then if the electron affinity of chlorine is greater than electron affinity of fluorine, then obviously from this relation, I can simply say oxidizing power of chlorine must be greater than the oxidizing power of fluorine. Yes or no? Naturally, the one who loves the electrons more oxidizes more your neighboring element, and you oxidize the others, hence you are called an oxidizing agent, and you reduce yourself. Right? And what is the question in the exam? Now watch carefully the way I'm framing the point here. Oxidizing power is basically the ability of pulling electrons from your neighboring atom, your neighboring substance. And that should be, you should be having love. And you can see here the oxidizing power is function of electron affinity. It must be function of what? Electron affinity, love. Then I think if you see the relation, Oxidizing power is greater than what? Oxidizing, you see, is directly related to electron affinity. And we know, we very much know that the electron affinity of chlorine is greater than electron affinity of fluorine. In fact, we are telling that electron affinity of chlorine is the highest in the periodic table, So you see that the electron affinity of chlorine is greater than what? Electron affinity of fluorine, right? And then naturally, it implies that the oxidizing power of chlorine must be greater than what? Oxidizing power of fluorine. Then it continues. But let me tell you that this is again an expected trend. This is the expected thing, obviously. But the real trend is a discrepancy again. The real trend is something else. It's reversed. And it's a discrepancy. And discrepancies are questions in exam. They are questions in exam. So what is a discrepancy? Then in fact, you must understand, in fact, I would like to say that the oxidizing power of fluorine is in fact greater than what? Oxidizing power of chlorine. This is too much. This is the real trend. And that's a question in the exam. Let's put things in proper way. Well, oxidizing power depends on your love towards electrons. And the love towards electrons is nothing but electron affinity. So greater the love, greater is what? Oxidizing power. That's what I have written. It's a direct relation. Then obviously people will ask you, that means that are you telling me that electron affinity of chlorine is in a way greater than electron affinity of fluorine, which is true. And then the oxidizing power of chlorine is also greater than the oxidizing power of what? Fluorine. In the obvious case. That's what is expected. But if you look into the real trend, in fact understand that it's oxidizing power of fluorine not only greater than chlorine, but it's rather greater than what? Chlorine, you must understand. In fact, I would like to tell you, in fact, fluorine is the best oxidizing agent. You must understand this. It is the best oxidizing agent which reflects in the properties. I would like to quote some of the properties and compare it with what? Chlorine. And you judge for yourself that, oxidizing power of fluorine is greater than chlorine, and we need to answer that. Why? Why such a discrepancy? Well, you understand that, when we singularly speak of one point and you have a discrepancy, it's not that case, then you understand that it's not this is wrong. Don't think that this is wrong. But there are other factors which are actually influencing what? This oxidizing power. And oxidizing power now not alone depends on what? Electron affinity or love. So there are other factors. It's a common sense. So common sense is telling us, even though what we are telling all this is this, correct, but if you see the trend which is reversed, indicating that there are several other factors which influences what? The oxidizing power. You must understand. Right? And first what we will do, we will justify that the fluorine is a better oxidizing agent compared to the others. And let's see. Then we will answer why and what. Let's see. Let me tell you first of all that, let's see. Let me put the question properly for you. Even though, I put it in inverted commas, even though electron affinity for chlorine greater than fluorine, still fluorine is a better oxidizing agent than chlorine. We need to answer why. Before I answer why, Let us justify that fluorine is a better what? Oxidizing agent. Well, I give an equation. Justification for fluorine better what? Oxidizing agent. Here comes in one example which I am giving it to you. Watch. Look into this equation. If you actually look into the reaction between methane and fluorine, and let us compare methane and chlorine. Methane and fluorine, and methane and what? Chlorine. And look into this. Not only methane, you take any organic compound, methane, ethane, benzene, whatever, any hydrocarbon you take, treat it with fluorine, straight away you get HF. And the carbon is reduced to C. Loss of hydrogens is reduction. So what is happening here? Fluorine readily oxidizes carbon, readily oxidizes methane, readily oxidizes methane to carbon. Methane to carbon. Loss of hydrogens is oxidation. So you look into this equation, the moment the fluorine is exposed to methane gas, you straight away got carbon. And all the hydrogens went away with fluorines. Remember that loss of hydrogen is also oxidation. You can see that the carbon has lost all the 4 hydrogens and it is oxidized to what? Carbon, making it a powerful what? Oxidizing agent. Look into this methane with chlorine. It gives a lot of things. It goes very slow, and this reaction is absolutely spontaneous. It's spontaneous rather. It's spontaneous. It readily occurs. But look into this reaction. It gives all sorts of nonsense. This first will give you CH3Cl. Then further it gives you CH2Cl2. And then it gives CCl4. And then it gives CHCl3. And then final product will be CCl4. You must understand this. So the reaction is slow. The vigorosity with which fluorine oxidizes, the hydrocarbons, you can see straight away to carbon, whereas you don't get carbon at all in what? Chlorine's reaction. Rather, they are giving this, and no carbon at all. You must understand. Making fluorine a powerful what? Oxidizing agent compared to what? Chlorine. You have n number of equations like this, and let us give the reason for that. So the truth is, even though electron affinity for chlorine is greater than fluorine, still fluorine is a better oxidizing agent than chlorine, and we have to give the reason. This is the justification. What I'm giving, that fluorine is a better what? Oxidizing agent. Now let us reason why such a thing will happen. Right? Why such a thing will happen. Right here. Let's explain this. Explanation for what? For fluorine being a better what? Oxidizing agent. Let us see. Why fluorine is a better oxidizing agent than chlorine? That's the question, and we have to give the reasoning for that. Remember that. Now if you look into this, electron affinity of chlorine is greater than fluorine. Electron affinity of chlorine is greater than what? Fluorine. Right? The love for electrons for chlorine is greater than fluorine. But still, chlorine is a bad what? Oxidizing agent compared to what? Fluorine. We are giving that explanation. But I wanted students to recollect what is electron affinity. What is electron affinity? Electron affinity is energy released when electron added to a neutral gaseous atoms. I'm underlining here. It's neutral gaseous atoms. So he is asking us, what is electron affinity? The electron must be added to an atom. Then it catches hold of the added electron and it exhibits its love. That love is called what? Electron affinity. That's what is told in the definition. But the issue is here, the issue is, to exhibit love, first of all, electron affinity comes later. Comes later. But first, let you dissociate to atoms. Dissociate to atoms. You don't have fluorine atoms, you don't have chlorine atoms, mind you that. Fluorine atoms and chlorines are not available. They are available as molecules. And remember that electron affinity comes later. We will discuss later. But first you convert yourself into atoms. First you convert yourself into atoms. First you do that. And when you do that, then I think you must dissociate now. The chlorine, which is having a single bond, must be broken to 2 chlorine atoms. That is how it is. And the fluorine, which is, these are molecules. These are molecules. They must be first cut forward into atoms and to fluorine atoms. This must be the first one. Then you try to add. Then if that is the case, this is a question, well, to break this, I think if you look into the bond dissociation energies, trend, well, look into this. Chlorine has the highest, rather, compared to even bromine. Compared to even fluorine, you must understand the fluorine is kicked to the 3rd place. And if I remember, this is somewhere around 58 kilocalories and this comes to 26 kilocalories. 26. So you have least bond dissociation energy for fluorine. So what fluorine is doing basically is, first of all, since it is a molecule, it is breaking itself into atoms because you require only 26.5, and I am ready. And I am ready as what? Atoms. I am ready as atoms. And then I am loving it. And then add the electron and form F minus. This is electron affinity. Whereas chlorine struggles. To break this, you require 58.5 kilocalories to get this, and you are basically struggling. You are basically struggling to break your bond. Then comes what? Electron affinity. So electron affinity is secondary. It comes second. First you break into atoms, because after all electron affinity is nothing but what? You add the electrons to what? And atoms, not molecules. And atoms are not available for what? Fluorine and chlorine, you must understand. They are not available. First you need to get into what? Atoms. And the bond dissociation energy of what? Fluorine is 26. It's almost half. But the loves compared to fluorine and chlorine towards the electrons is slightly 2-3 points down. That's all. Both are lovers. Both are lovers, except for fluorine is a better lover compared to fluorine. But still, first of all, you should convert to atoms. You are not doing it because chlorine is struggling because it is 58.5. And it is half is what? Chlorine. So if you just say, yeah, just like that, you have your atoms ready, and the fluorine is adding the electron and making fluorine a powerful what? Oxidizing agent, you must understand here. Right? That's what is the explanation, and that's what it is.